Hi everyone, for my journal article I decided to go over one titled Time-Integrated Thermal Bleaching Thresholds of Reefs and Their Variation on the Great Barrier Reef by Ray Berkelmans. Firstly, I'd like to go over what coral bleaching is exactly, and it's defined as a loss of pigment in coral due to symbiotic algae, specifically zooxanthellae, exiting when environmental conditions are harsh, and it can eventually lead to coral death. So this is what coral normally should look like. It's very colorful, very vibrant, and this is what it looks like when it's been affected by coral bleaching. In hopes of mitigating the effects of coral bleaching, we need to know the factors, which we'll get into later. We also need to determine the impact thresholds, which are the conditions in which no bleaching is predicted to occur. And we also need to know the changes in global climate. But it's difficult to predict these patterns because multiple stressors might act simultaneously, and severity of bleaching is variable to exposure time, species, and location. Now that we know the basics of coral bleaching, we can get into Berkelman's findings. He states that there's 4 main factors that may contribute to coral bleaching: sea surface temperature, wind speed, solar radiation, and barometric pressure. In order to identify the main contributor to bleaching, he collected records for 13 locations along the Great Barrier Reef in the past 10 to 12 years. He chose to just consider the months January to March because that's the time for peak bleaching to occur in Australia. He then scanned and averaged the data he compiled every 30 minutes and compared those values to the values from the 1998 bleaching event. He also wanted to develop a formula to predict when coral bleaching is expected to occur based on average daily exposure temperatures. He did this by calculating the cumulative time at each temperature during Australian summer and creating a polynomial bleaching curve. The position of this curve between the warmest non-bleaching year and the coolest bleaching year was estimated based on a formula which used a 5-point scale, with 1 being the most severe and 5 being the least severe coral bleaching. This is a table he created, clearly showing the bleaching severity score on the right in the 13 locations along the Great Barrier Reef. Now we can get into the results. These 2 graphs show data for 2 reefs that Berkelmans collected in that 10 to 12 year period. The top parts of the graph show monthly sea temperature as the bar and wind speed as the line, whereas in the bottom parts of the graph, solar radiance is seen as the bar and barometric pressure is seen as the line. In February of 1998, which is shown as the black bars here, that was the height of the bleaching event that happened in the Great Barrier Reef. And the main significant difference between that month and the rest of the months that followed or were prior to that is that the temperatures here were the highest that they've ever been. Next, we can look at how accurate Berkelman's bleaching curve was in predicting bleaching patterns. The bolder line here is his predictive curve, and then the thinner one here is the recorded observations. And just 4 years were used to collect data for this curve, but it's still really close to the other one. And it's negatively sloping because as temperatures rise, the coral's exposure time decreases. And therefore, we can conclude that sea surface temperature is the strongest contributor to coral bleaching because of the significantly higher temperature during February of 1998 than the rest of the months that were recorded. And the remaining factors didn't show that strong of a correlation with coral bleaching pattern. We would expect wind speeds to be low when coral bleaching happens, and they were during 1998, but not as low as they were in 1992. And also solar radiance was normal throughout the recordings. Barometric pressure was high, but it was recorded to be higher in past years. Variation in some bleaching curves could suggest that some coral are going through thermal adaptation, but there's not enough data to confirm that yet. And with more on-site temperature data points, we can predict a more reliable bleaching curve.